let's take a look now at coordinate vectors. And so to understand what we mean by coordinate vectors, let's recall a theorem that we had in one of the previous videos. We had the following theorem that said, well, if t, and this is kind of, it's not really a recollection because I'm restating this theorem, but we've talked about a theorem very similar to this theorem. So if we have a linear transformation t from Rn to itself, then this transformation is an isomorphism if and only if t maps a basis of Rn to another basis of Rn. Okay, so we had this theorem that said, if you have an isomorphism, it takes a basis to a basis, right? But now we're specifically looking at maps of Rn into itself. And these maps are isomorphisms of Rn if and only if it takes a basis of Rn and it maps it to some other basis of Rn, right? And so again, we've seen something like this theorem, but here's the result specifically for maps of Rn into itself. And now we want to ask, okay, well, let's say we have some basis for Rn, like maybe we have the standard basis E1 through En. And under the map T, there's some arbitrary basis V1 through Vn, right? You don't always have to start with the standard basis E1 through En, but just for an example, let's think about this. So if we have, right, you could map an arbitrary basis and see what the image of that basis is, and then that would be also be a basis if you have an isomorphism. But just for an example, and to build some intuition, let's say we're looking at first, we map the standard basis into, and then we get some arbitrary basis, V1 through Vn. So what would that look like, right? Well, let's do an example when T is a map from R3 to R3. And let's say we have that E1, E2, and E3 are mapped to some other basis, V1, V2, V3, like this, okay? Now, what is E1, E2, E3? Well, this is just I hat, J hat, K hat, right? So we have I hat, J hat, K hat here. This is your E1, E2, E3. And then we describe some vector. Let's say X. We describe this vector in the standard basis as X equals, it's some number of units like X copies of I hat, or X units in the X direction, right? Plus Y J hat plus Z K hat. This is how we describe vectors as a linear combination of standard basis elements, right? Like it's a linear combination of I hat, J hat, K hat. You can describe all points in R3 or all vectors in R3 uniquely by this combination, right? And we write this, we drop the I hat, J hat, K hat, and just write this as the vector X, Y, Z. But now let's suppose we want to understand the same vector, but in this new basis, right? So maybe we have some new basis like V1, V2, V3. And you may ask, well, what is V in a different basis, right? How could we understand the same vector, but in a different basis? Well, this is the notion of a coordinate vector. So the answer is a coordinate vector. Okay, so let's see what we have here. give a definition. Let's let B, which is a basis V1 through Vn, let's let this be an arbitrary basis, of Rn. And then let's let X in Rn just be some vector. Then, well, if V1 through Vn is a basis, that means we can write X uniquely as a linear combination of those basis elements, right? Then we can write X equals A1 V1 plus A2 V2 plus et cetera, plus AN Vn, right? And then we define the, well, let's define the coordinate vector. And we write CB of X, or X sub B, right? We're just saying with respect to what basis. And this is described as CB of X, which is CB of A1 V1 plus A2 V2 plus et cetera, plus AN Vn. We just write this as A1, right? We take all the coefficients, A1, A2 down through AN. And then this is with respect to the basis B. So it's implicitly understood that we're using our basis V1 through Vn, right? And not just the standard basis here. And what does this mean, right? Like what this means is then we're describing in this example from R3 to R3 that we were looking at here. Well, then we would be writing X as now say like A1 V1, where it's no longer this X I hat plus Y J hat, right? We're describing the same vector, but in a new coordinate system. So A1 V1 plus A2 V2 plus A3 V3, which would look like A1, A2, A3, and then B if we called this set B, right? And so you can see this description of X and this description of X are inherently different, but they're telling you the same information. It's just with respect to what coordinate system or what basis you are describing that vector. So let's look at an example, like a more explicit example here, right? So let's say we have a basis for R2. So this is an example. We have a basis for R2 given by 1, 0, negative 1, 1, right? This is certainly not the standard basis on R2. And we know X, let's say X is the vector 3, negative 1. And this is 3, negative 1 in the standard basis, right? Meaning when you look at a picture here, X, Y, we know the vector 3, negative 1 is 3 units long in the X direction, 1 unit tall, right? Or sorry, negative 1. So how about 1 unit down? Let's back that up. Right, and so this would be our vector X here. But we want to describe X. Let's find CBX, which is describing this vector X in terms of as a linear combination of basis elements in this different basis here, right? So what do we need? We need that to find CBX. This means we need to find A1 and A2 such that 3, -1 is equal to A1 times the first basis element plus, I'm going to come down here for more room to keep room for the graph there, plus A2 of the second basis element, -1, 1, right? And you can see here, well, to find the coordinate vector with respect to this basis, we just need to solve the following system of equations. 3, -1 equals A1, 1, 0 plus A2, -1, 1. We have a system of two equations with two unknowns. You can solve this system using reduced row echelon form, et cetera, or you can do it by inspection and see that A1 is 2 and A2 is -1, gets you the solution that you would like, right? And so this means CB of X is 2, -1. What does this mean, right? What does this mean, this coordinate vector here? Well, when we have X described in terms of the standard basis, and maybe I should say B here, right? Because it's understood that this is with respect to a different basis. When we have E1 is 1, 0 and E2 is 0, 1, what does this notation 3, -1 mean, right? It means you take 3 copies of E1 and then plus -1 copies of E2. Right? That's negative E2. And the vector 3, -1 is the result of 3 times E1 plus -1 times E2. What does this mean in the new basis, right? In the new basis, we have, well, the first vector is still E1, but the second vector is the -1, 1. So let's go back 1, up 1. So this would be, let's call this V1 and V2 here. So this would be V2, right? And what we're saying now is the vector X, this is described as 2 copies of 1, 0 plus or -1 copy of -1, 1, right? That's exactly what finding this coordinate vector meant. So if we take 2 copies of V1 and then -1 copy of V2, you can see we get the vector X there, right? You can still see that if you take 2 copies of V1 plus -1 V2, you still get the vector X. And so even though they are different vectors, with respect to a given basis, it's describing the same vector here, right? And so this is exactly what a coordinate vector is doing. It's giving you a way of how do I describe a vector in a different basis? And that can be very important because depending on the context, maybe arithmetic is easier in a different basis, right? So let's see what else we have here. We have a theorem that says if B is any basis of Rn, then the function CB, which is a map from Rn to itself, is an isomorphism. Well, sure, right? The first theorem I had in this lecture was saying that if you have a linear transformation of Rn to itself that takes a basis to a basis, then you have an isomorphism. Well, by definition, that's what the coordinate function is doing here, right? CB is taking a basis, right? Or it's taking a vector that's a linear combination of basis elements, and it's spitting out the same vector that it's a linear combination of new basis elements, which means that it's mapping basis elements to basis elements. So therefore, it's an isomorphism. Let's look more generally here. If we have a linear transformation from Rn to Rm, not necessarily of the same dimension, that's a linear transformation. And let's let B1, this will be a basis of Rn, and B2 is a basis of Rm. Okay. And let's give the basis B1 a name, or let's describe it in coordinates. So that's V1 through Vn, or not in coordinates, excuse me, but element-wise, right? We're giving an element-wise description of B1. We'll say it's V1 through Vn here. Then we have the following equality. We have that the function CB2 times T is the same as M, or composed rather, right? MB2 B1 C B1. So let's quickly understand. Well, first let me say where we know what CB1 and CB2 are. We know what T is. Where M, we don't know what MB2 B1 is. This is a matrix defined as CB2 of T V1. In the first column, you know, CB2 T V2. In the second column, et cetera, all the way to CB2 T Vn, not of, right? About sub n in the last column, or in the nth column here. So where this will be a unique m by n matrix, right? What does this mean here, right? What is this telling us? Well, what this is telling us is, let's look at the following picture. We have Rn is being mapped to Rm via T, right? In both spaces, in the domain and the codomain, we have coordinate functions that maps a basis of Rn to another basis of Rn. This will be our C B1, right? That's exactly what CB1 is doing. If B1 is a basis for, if CB1 is a basis for Rn, or if B1, excuse me, is a basis for Rn, then CB1 is mapping a basis of Rn to a basis of Rn. Similarly, CB2 maps a basis of Rm to Rm. But then we also have this matrix, MB2 B1, right? This is a unique m by n matrix. So we can think of m by n matrices as transformations that take Rn to Rm. And what we're claiming is that this square commutes, meaning if you first go C1 or C sub B1 followed by MB2 B1, which is what we have on the left here. That's exactly this composition, right? It's C1 B1 or CB1 first, followed by M2 B1. That is the same as going first T from Rn to Rm, and then CB2 from Rm to itself. And that's exactly the left-hand side of this equation here. And this is called a commutative diagram. We get this commutative diagram here of linear transformations. And basically what we can think about MB2B1 as being is we can think about this being a matrix that transforms vectors in Rn with the basis T of, or CB1 to vectors in Rm with this new basis CB2, right? So that's what we're looking at here. So we can figure out how to find this kind of transition or coordinate matrix here. So let's do an example. Let's say we have a transformation from two-dimensional Euclidean space into itself here. So T is from R2 to R2. And then let's define this by T of AB equals BA, right? So we're just flipping the X and Y components here. And let's first define a basis of R2 as 1, 0, negative 1, 1. And let's define a second basis of R2 as 1, 1, 1, negative 1, like this. And now let's say we want to find the transition matrix here. Let's find MB2, B1. Okay, so how would we do this? Well, to find this matrix, well, one thing you can think about is take this equation and multiply on the right by CB1 inverse. We know it exists because CB1 is an isomorphism, right? And so really what you could get here, if you'd like to see the map explicitly, I'm just going to write it, let's say in yellow, I'll write it in here. Really, MB2, B1 is equal to CB2T, CB1 inverse, right? That's exactly what we're doing here. I won't be so explicit, right? But that's what we're doing. So in this example, what do we need to find, right? We can also think about this MB2, B1 as just this matrix here. Oh, let's use a different color. In gray here, right? We just need to find the CB2 of TV1. So first we need to find TV1 through TVN. Okay, so this is going to be our V1, V2, and we need to find the image of these basis elements under the transformation T. Well, what's TV1? TV1 is going to be T of 1, 0, which is 0, 1, right? Because based on how our transformation is defined, it takes elements in R2 and inverts their coordinates, or not inverts, but it flips their coordinates, right? And then we need to find CB2 of TV1, right? This is the first column of the matrix MB2, B1. Well, how do we find the coordinate vector for 0, 1? Well, we have to look in the new basis, right? Because we're in B2. So that means we want that 0, 1, right? To find this, we want that 0, 1 is a linear combination of elements in the second basis here. So that would be A1 times 1, 1 plus A2 times 1, negative 1, right? That's how you find the coordinate vector in this case. And you can see if we let A1 be 1/2 and A2 be negative 1/2, we would get exactly what we want. So what we've learned is that CB2 of T of V1 is equal to 1/2 negative 1/2. Okay, there's the first column of the transition matrix that we're looking for. Now let's find the next column. So we want T of V2, which is T of negative 1, 1, which is going to be 1, negative 1. Now we want to find the coordinate vector with respect to the basis B2 of T of V1, or T of V2, right? Which means we need to find coefficients. Let's say we used A1 in the last, so let's say B1 times 1, 1 plus B2 times 1, negative 1, such that this is true, right? Well, this would be true when B1 is 0 and B2 is 1. So if that's the case here, then CB2 of T of V2 is going to be 0, 1. And this will be the second column of our matrix, right? So we had CB2 of TV1, and now we have CB2 of TV2, which means juxtaposing or augmenting these column vectors into a matrix gives us MB2, B1 is the vector or the 2 by 2 matrix 1/2, -1/2, 0, 1. And this is how you find the transition matrix here between the two bases B1, B2. All right, so this is where I'm going to break for now. And next, we're going to wrap up the discussion of linear transformations by looking at generalized solutions to systems of linear equations. We'll see what it means for a solution to be a particular solution, and then what it means to construct a general solution from elements of the null space.